DES was a big stepping stone and is also the foundation of modern hash functions. In this lecture, we're going to see exactly how it works. And this is where we left off in our last lecture. So in this lecture, we focus here, specifically how we are applying the Feistel function and what is going on inside of this process. So in this picture, each blue dot represents 1 bit. So in shuffle and expand step, we're expanding our bit count up to 48 bits. And this expansion is necessary since in our next step, this reduction back down is partly how we're going to break the linearity. So back to the shuffle and expand. You can also see a small flavor of, the small flavor of shuffling the location change. It is small, but it is happening. And to the substitution box, DES uses 8 of these boxes. You can find the definitions of them in the DES protocol. And I just picked box 5 for us to take a close look at as our example. And this is a close-up of box 5. And we have our 6 bits coming in and 4 bits that are going out. And it is one of these 4-bit series that will be our output. So to use an example, so we have our 4 bits. They went through the shuffle and expand, and they gave us this 6-bit value. So the first and last input bits are both 0. So that puts us here in this column, or in this row. And the middle 4 input bits are 3 zeros and a 1, which puts us here in this column. And there are also 4 other input combinations that would give us this same output. And this is very much by design. This is intentional. So if you take just our example here, we have our output. And if you try to trace this output backwards, these are the different input options. And combined, or on average, you can see that there is the 50-50 chance of these outputs being a 0 or a 1. So for each individual output bit, we still have the 50-50 chance of a 0 or a 1. And then additionally, each of these bit outputs is also going to be influenced by its neighbors as they go through the sub box. And we have been reduced back now to 32 bits. So these are the same bits that came out of the substitution box step. And this is what the shuffle number 2 looks like. So this is what a single iteration has, these moving pieces, plus DES uses a 64-bit random secret key. So for each iteration, there's a smaller key called subkeys. And all of these are just slightly tweaked versions of the original. So recall after shuffle 1, we're sitting at 48 bits. This is where the key is added in. So now I had to turn the image sideways so I could fit it all on this page. But this is how the key is fused in for each iteration. So we have the 48 bits from our expansion, the 48 bits from our key schedule. They go through a common process called XOR, which is a method that combines like sizes together, leaving us with the same size output. And these 48 bits are now what go into the substitution boxes. And here's a bit more technical look at this. So this table really is your source on how to see it. We have 2 inputs, blue and red, and their combination will just produce a single output. Again, keeping our total bit count to 48. And so now this is the complete picture of a single iteration within DES. We have a total of 16 iterations or layers of our sandwich. In each iteration, the input and output bits get their link broken. So each Feistel segment is mixing around the various inputs across the 8 different designs of substitution boxes. And at the end of 16 rounds, the resulting ciphertext has no patterns. and there are no one-to-one links between the individual inputs and outputs. So Alice now can perform her encryption to include her secret key, and her ciphertext as her result will look just like a random number. Bob reverses the process, and with this shared secret key, he will recover the plain text. And this secret key is so large and random that it is impossible to exploit patterns, and it is impervious to brute force, ensuring no one else except the secret key holders can read the plain text. Now, DES was the first application of the Feistel process, but more than that, this capability was the foundation for a whole new cryptographic tool of hash functions.